Okay, so if you haven't turned in work on the related rates test, you might want to do that. If you need break to finish it up, you can, but I'm putting it in the grade book today. So if you turn in work, I'll try to get it graded before today. If not, I'll grade it when we get back, and I'll update it then. Okay, so we were looking at some rational functions. Right, here was one where, give me thumbs on this. Everybody understand that the limits at infinity on this one are going to be 0 for any number of reasons, right? You can do it because the bottom has a higher degree than the top, so you know it automatically. The limit of the function is the same as the limits of the ratio of the leading terms. So I just get the limit of 3x over x squared. If I simplify that, I just get 3 over x. So as x goes to infinity, that's going to go to 0, right? Because the bottom is huge. Or you can use L'Hopital's rule and just differentiate top and bottom separately until it's no longer indeterminate, which is only one time, right? If you differentiate once, you get 3 on the top and you get 2x on the bottom, and so you get 3 over infinity, so you know it's 0. Either way, you get the limits are going to be, let's write that in, the limits at the infinities are 0.
So why did you take the limits on this one?
Well, because ultimately what we're going to be doing with this stuff is sketching it, right? And that's your next test is going to be just making tables and then producing a sketch. You know, just that's all it's going to be. So we want to know what the asymptotes are, horizontal and vertical asymptotes, if we have any, because it makes it super easy to sketch the function, right? If you know what the behavior at the tails is, the end behavior, and then the asymptotes. Yep.
Do we have to sketch like each derivative, like all of it?
No, you're gonna use your table to just sketch what the
Part though, like what's the original function?
the original function. Yeah, right. And then we said, remember also that if we factor the bottom factors into x plus 1 and x minus 1. Or you don't even have to even factor it. We just know the zeros of the denominator are plus and minus 1. And those are unique zeros of the denominator, which makes those vertical asymptotes. Anytime you have a value that makes the bottom 0 and the top non-zero, then that's guaranteed to be a vertical asymptote. So in our table, look what we get. We get these places where the derivative is undefined. We can just write VA and put a dashed line there, and that's going to split this thing up into separate parts. It's going to kind of match the sketch we're going to make too then, right? You can see those sort of almost look like vertical asymptotes. When we did the derivatives, we found the first derivative was that when we factored it. Well, the bottom is 0 at the asymptotes. Those are not in the domain, so those are not critical numbers. Give me thumbs on that. Does that make sense? And there are no zeros of the top because the factor x squared plus 1 is never 0. It's always positive valued. So we got no first derivative critical numbers. When we took the second derivative and all the dust settled, we got that. And so the quadratic factor gives us no zeros, but 6x is 0 when x is 0. So we got one critical number from the second derivative, and that's it for this entire function. So this was our table. Okay, we just need to complete it. So now what? What do we need to do? And there's 3 completely separate sections of this function, right? Anytime you have vertical asymptotes, it's breaking this thing up into separate universes that are completely disconnected. So how would I know what's going on to the left of this asymptote at -1? Yeah, I just do a test point. Yeah, absolutely. So I'll pick a point like -2, for example. Okay, if I pick -2, what do I want to know?
The sign of the second derivative.
Okay, we could do second derivative. You could do either first or second derivative. You're going to find out that it's unambiguous. They're both going to tell you the same thing. If we try the second derivative at -2, what's the sign of the second derivative at -2? It's going to be negative, isn't it? Everybody agree? At negative 2, we're going to get negative times positive over positive, right? So we get negative. Okay, what's that tell us? Now think about, look at these asymptotes we've got here. We know I've got these vertical asymptotes, and I've got a horizontal asymptote over here at 0. So what can this thing do? Not much. It's only got 2 options, doesn't it? It's either doing this or it's doing that, because there are no critical numbers. There's no extrema, so it's very simple. Well, we found that it's concave down, so we know it's doing this. Right? Has to be. How else could it stick to those asymptotes and be concave down? So what's the sign of the first derivative guaranteed to be if we test it? Negative, because it's decreasing, right? And that's what it would be. If we plug in negative 2 in our first derivative, yeah, I'm just going to get negative times positive over positive, right? In fact, what's the sign of the first derivative above, like at positive 2? Negative, yeah. So if we go out here to positive 2, right? So then what's the function doing over here to the right of this vertical asymptote at x equals 1 if it's negative?
Wouldn't it be the same thing but on the top?
Yeah, if it's going downhill and it's got to stick to these asymptotes, doesn't it have to do that? See what I'm saying? Right? You see that it couldn't bend the other way, because then it wouldn't be asymptotic. Right? Everybody get that? Like, everybody sees that, right? So then we haven't tested it yet, but what's the sign of the second derivative guaranteed to be to the right of positive 1? It's got to be positive. It's concave up, and that's guaranteed. That's what we'll find.
How do you know the horizontal asymptote is 0?
Because we took the limits of this rational function as x approaches the infinities. Right?
So if it's higher degree on bottom, there's a horizontal at 0?
Yeah.
Okay.
Okay, so let's,
Oh, I know.
you remember this stuff?
Yeah.
Okay. And then if we test the second derivative at positive 2, look what it's given us. Positive times positive over positive, right? So it's positive. Like we said, it's concave up. Okay, now what are we going to do in the middle, that section between the vertical asymptotes? What are we going to do in there? Okay, think about that for just a quick second. Okay, so what's the verdict? What are you going to do? Yeah, so what values? 1/2 and negative 1/2? Okay. And what are we going to test here? Second derivative, because we have a second derivative critical number there, so we need to know if that's an inflection point. Okay? Okay, so we'll try negative 1/2 and positive 1/2. In the second derivative, where's that? Oh man, is it doing this? Of course. Okay, so we were checking second derivative, right? At negative 1/2 and positive 1/2. Well, what's going to happen? At negative 1/2, that's going to be negative, positive. What about the bottom? Negative, yeah. So negative over negative is positive. Okay, so we got here we got positive concavity, and then at positive 1/2, it's going to flip, isn't it? Because the bottom's going to stay negative, but that's going to be positive now. Okay, so what's that doing? It's going from positive concavity to negative concavity while sticking to those asymptotes. And if I plug 0 in the function, what do I get back, by the way? 0, yeah. Right, so we get the point 0, 0 down here on my function. And what's it doing? If it's positive concavity to the left, yeah, it's got to be doing this, doesn't it? It's got to be going like that. Does it actually ever have a horizontal asymptote? Let me draw that again, because it almost looks like I drew it with a horizontal asymptote. But it doesn't, does it? We know it doesn't. How come? Because the first derivative would have had to have been 0 then for it to have a horizontal asymptote. And it doesn't, right? So then this thing actually has to look like this. Make sense? How do I know that it doesn't dip down and come back up and go down?
Because of the degree?
Well, I mean, you probably could figure it out that way, but there's a lot easier way. If it did dip down and come back up, what would it have had to have had? It would have had to have 2 critical points in there, and it didn't have any critical numbers, right? First derivative critical numbers. So we know that's what it has to do. So that's our sketch. Okay, make sense?
Why does it pass through
What-
horizontal asymptotes?
Why did, okay, because horizontal asymptotes don't mean anything in here. Horizontal asymptotes are only meaningful at the infinities. Right, you can pass through a,
There's a vertical asymptote that doesn't do it.
right, you can't pass through vertical asymptotes, but you can pass through horizontal asymptotes. And I actually showed you guys an example of like a harmonically damped function where it was a sine function that just got smaller and smaller forever, so it passed through it an infinite number of times, but it still converged on y equals 0. No, it doesn't have to be. I mean, this could have in the middle, this could have been like a minimum or something that passed through it, yeah. Okay, good questions. All right, so now here's the other one. This is on your side. Oh, and then were there any other questions on this? I think we already talked about symmetry, didn't we? We said it was odd over even, so it's odd symmetry. Domain would just be everything except 1 and -1. Okay, what about this one? This is kind of a tricky one. So this is where we got to start being really smart about these functions. That is a pretty ugly looking rational function. If I just differentiate that using the quotient rule, just think what that's going to be like. I'm going to have low d high. Well, d high is going to be a cubic trinomial, or a quadratic trinomial. It's going to have 3 terms, minus high times d low, which would be a binomial. That's a lot of distribution and collecting like terms to make a really big, ugly polynomial that I would then have to factor on the top. You see how that's a lot of work, right? So, I mean, it would work out, but man, you're doing a lot of work there. So what we should do instead, we're going to have to find the domain anyway, right? So we need to find the zeros of the denominator. Fortunately, the denominator factors pretty easily. What does the denominator factor into? X minus 4 times x plus 1, okay? Now the top does not factor easily, does it? You can't group it exactly because it fails the ratio test, right? Because the ratio of 1 to -12 is different than, right? The top is not going to factor using grouping. If it did, it would have been pretty easy to factor, but it doesn't. So we're going to use synthetic division. Now, rather than just randomly picking values or even using the rational root theorem, what are the factors that we're really interested in seeing in the top? Yeah, well, x minus 4 and x plus 1, right? We need to know because already we can see that there are some values that we have to exclude from the domain. X cannot equal 4 or -1, right? But we don't know what's going on there yet. If those are zeros of the bottom but not the top, then they're vertical asymptotes. But what if they're zeros of both the top and the bottom? Then it's indeterminate. If I tried to evaluate, if I try to take these limits, for example, let's just say that 4 is a zero of both the top and the bottom. If I try to evaluate this function at 4, I get 0 over 0, which is indeterminate, right? Does that make sense? So then we'd have to resolve that either by, like we did at the start of the year, by canceling like factors in the top and the bottom, or we could use L'Hopital's rule if we wanted to also, right? But we want to know, first things first, we want to know if either one of these is a factor of the top. So how do we check? Well, we're just going to run them through synthetically and see. Okay? So let's do that. Okay, so I want to remind you guys about a trick I showed you a couple years ago. Remember I showed you this kind of a abbreviated, it's like a tabular synthetic division where you can try a bunch of different numbers at the same time. And it was really useful when we were doing the rational root theorem. Remember what that said? If we want to find all of the rational zeros of that polynomial on top are going to be built from factors of the constant divided by factors of the leading coefficient, right? So all the different factors of 64 would make the numerator of those rational numbers, and all the factors of 1, which is just 1, would be in the denominator. So all the numbers we could get would be 1, 2, 4, 8, 12, no, not 12, 16, etc., right? 32. We have to try all plus and minus all those synthetically. But we're not doing that. We don't have to find all of them. We just want to know if either one of these works. And if one of them does, then when I factor that out, I'm going to be left with a quadratic trinomial, which I can just factor or use the quadratic formula for, right? Make sense?
So why are you only testing for the 4 and negative 1?
Because I need to know what these things are. Are these going to give us vertical asymptotes or holes? So we have to know anyway, right? So let's run this thing through. So here's how we do it. We make a vertical line, and then on top of the table, we're going to put all the coefficients of the numerator. So we get 1, negative 12, 48, negative 64. And then we put another vertical line right here, which counts as the remainder box. Remember doing this? And so we're going to try, for example, let's try negative 1. If we try negative 1, the only things we write in this table are just the things that would show up underneath the synthetic division bracket. So what do? We drop the 1 down, right? And then what? Anytime a number drops down, we multiply by the number out front and add to the next number, right? So I get negative 1 plus negative 12 is negative 13. Negative 13 times negative 1 is 13 plus 48 is 61, and it's not going to work, right? We can already see I'm not going to get 0 in the remainder box. So that one doesn't work. We could cross it out. Move on to the next one. How about 4? Bring the 1 down. 1 times 4 is 4 plus negative 12 is negative 8. I get negative 32, and 48 is 16. I get positive, whoops, I get 64 plus negative 64 is 0. So positive 4 is a 0 of the top also. Everybody get that? You see that? How that worked? Okay, so we also factored the top then, right? We know that x minus 4 is a factor. What's the other factor? So when I want to write the top, what else goes there? Yeah, right here. It's this stuff, right? That's the other factor. We're going to get x squared minus 8x plus 16. Everybody see that? Okay. And then on the bottom, we have x minus 4 times x plus 1. And look, we can algebraically cancel those. And so what's going on? What's going on? What's happening at negative 1? Vertical asymptote, right? Because negative 1 was a 0 of the bottom, but not the top. At positive 4, we had zeros of the top and the bottom. But now if I cancel those factors, all of a sudden now 4 is no longer a 0 of the denominator. So it is not a vertical asymptote, because we ended up with something that ended up, after we simplified that polynomial, 4 was no longer a 0 of the bottom. It turns out it is a 0 of the top. That's okay. That just means that the value of the function is 0. It's just it just goes through the point 4, 0. That's where the hole is. That makes sense? It wouldn't be, if I evaluate this at 4, I guess I get 5 on the bottom. So I get, 0 over 5, which is 0. That's the value of the function at 4. Is that making sense?
Yeah.
Okay. So, but the great thing here is, look, we can trade this function now for this guy. That's a lot easier. Okay. Oops. So we go back here, and we can say, okay, we'll call this a new function. G of x equals x squared minus 8x plus 16 over x plus 1. And that's the one we can differentiate, the simplified version. Okay? Yes?
Does it still have the domain restriction?
It does. You inherit all the domain restrictions, right? Because the original one, these had to be excluded. What did we do when we canceled those factors? Really all we did was we filled in the hole. So we just created a new function. This is the same function, except this one doesn't have that hole in the function at positive 4. Okay, but it has to be there because that's what the original function had. Okay, remember talking about this at the very beginning of the year? We spent some time on this. Okay, what does the top factor into, by the way? Yeah, x minus 4 squared over x plus 1. And so now let's calculate derivatives. So my derivative, this is a pretty easy derivative now, right? If we do quotient rule, we get low times d high. Well, that's just 2 times the quantity x minus 4 minus high d low over low squared, right? So x plus 1 squared. Everybody agree? So far, so good? Okay, what could we do in the top? Well, look, we could factor out, I have an x minus 4 in each of those two terms. So we'll factor out an x minus 4. And then we're left with, what's left behind? I'm left with 2 times the quantity x plus 1 minus x minus 4 over x plus 1 squared. See how much easier? Like that ended up not being a terrible derivative. It would have been really ugly if we hadn't simplified those, factored and canceled out like factors. Okay. What if there were no like factors? Then we're stuck, unfortunately, with that, right? So if let's distribute the 2 and distribute the negative 1 and combine like terms. X minus 4 times 2x minus x is x. 2 minus negative 4 is plus 6. So there's our first derivative. So where are my first derivative critical numbers? Negative 6, positive 4, right? Make sense? Is positive 4 actually a critical number, though? It's not. Okay. Because it's restricted from the domain, right? Right, so then we only get our only critical number is x equals negative 6. We take a second derivative, okay? So, second derivative. Okay, so low, d high. What's the derivative of d high? It's convenient here to think about this. We don't want to make it a product. Differentiating a product is kind of a pain. So let's just expand this out real quick. Isn't that just going to give us x squared plus 2x minus 24 if I expand that out? So what's the derivative of that? Yeah, 2x plus 2. Do you see the motivation for that? We don't want to have to do a product rule inside a quotient rule, right? It's easier just to expand that out. Minus high. Now this time, do we want to? I don't think we don't have any factors over here. We don't have any x minus 4s or x plus 6s. Everybody get that? So there's no reason for us to leave this factored, right, when we do high, D, low, because we're not going to be able to factor any of that stuff out anyway. So let's just go ahead and write it in its expanded form. Times the derivative of the bottom, D low, is just 2 times x plus 1, isn't it, to the 1? Okay, divided by the bottom squared. X plus 1 squared squared is x plus 1 to the 4th. Okay, now don't expand this out if you can avoid it. Do you see something good here? Rather than having to expand this whole thing out, can I factor out something instead? Yeah. In fact, look what this is. 2x plus 2. Isn't that the same thing as 2 times the quantity x plus 1? Yeah, look, I can take those out right there, can't I? Right? I can't do that because this one right here, remember this one didn't factor.
No, I'm saying like you have the one in front.
Yeah, I'll take all the red stuff out completely.
No, the blue too. What about the blue?
I can't take the blue out because I've only got an x plus 1 to the 1 in the second term. See what I'm saying? Like if this were squared, yeah, then I could take an x plus 1 squared, and I've really got 2x plus 1 cubed in the first term, right? But in the second one, I've only got one factor of x plus 1, so I can only factor out a single x plus 1 factor, okay? Okay, but that helps. We take out that 2 times the quantity x plus 1, and what's left behind? So all that stuff got taken away and all that stuff got taken away, right? And so then really what we've got here is just x squared plus 2x plus 1 minus x squared plus 2x minus 24. Everybody see that in the top? Divided by x plus 1 to the 4th. But look at this. I can cancel out one of those factors too. Okay? See how that works? Moral of the story being what? Factor the polynomials first. Yeah.